Okay, so the recording has started now. Now I'll share my screen. So hello everyone. This is like week 7 of NPTEL CS52 TA session of Reinforcement Learning course by Professor Balaraman Ravindran of CSE Department and IIT Madras. I'm Sandarbh from CSE Department IIT Bombay. And generally like these sessions are on Tuesday as usual. So let's begin with today's session. So like this is the link as usual, and anyone who has taken this course can attend. So like like similar to previous sessions, we will be discussing practice assignments and assignments. Also some problem solving, like these will be different from the practice assignments and assignments, and doubt clarification in case you have some doubt. And these sessions are mainly to enforce two-way communication. So as usual, the expectation is that you should have watched the weekly lecture videos of week 7 and at least made an honest attempt on the weekly assignment and the practice assignment. Also, it's recommended to read the Satin and Barto book, which was chapter 7 and 12 for this week. And the slides and recordings will be made available in the same like Google Sheet. So I hope like you guys have access to that Google Sheet. So these are the general guidelines. Keep yourself muted. If you have doubts, you can ask by unmuting or just write in chat and try to be responsive and try to solve the problem simultaneously. And if time is needed, I'll give you time. So the order will be as before: practice assignment first, then problem solving, then demo. So for today's demo, like there will be two demos. First will be like we will see how MLE is maximum likelihood estimate and map maximum a posteriori, and there is that full Bayesian concept in which like we will see how these apply in bandit setting, and we will like see the demo of Thompson sampling again, and then we will move to assignment. And the second demo will be regarding Sasa lambda. So we will see like both accumulating traces, also the replacing traces. So these are the like topics of week 7: eligibility traces, backward view of eligibility traces, then like forward view. I think like it was mentioned in the first section itself, but the equivalence you guys have to like derive it on your own from the book. So then we move to control. So then we saw like algorithms like Sasa lambda here and Watkins Q lambda algorithm. And there was some recap on Thompson sampling, which included MLE estimate, map estimate, and also like full Bayesian. So okay, let's begin with today's session. So first, practice assignment as usual. So here they are asking which of the following is equal to GT of 3. So they are basically asking three-step return. What is the formula? So is this like three-step return? First one, RT plus 1 plus gamma times RT plus 2 plus gamma square times. This is actually two-step return, right? And this will be denoted as GT of 2. So this is not the answer. Is this the three-step return? Like this seems correct. Gamma, gamma square, then gamma cube, and rewards are also correct, and the state is also correct. So this is the correct answer. And the issue with this one is that like here instead of ST plus 3, they are having ST plus 4. So that is the issue. So this is also not the correct answer. And simultaneously, like if option B is correct, then this cannot happen. So this is like purely definition based. I hope like you are able to get this answer quite easily. So if you have watched just the lectures, you will be able to get this. So now moving to second question. So this is true or false. So the idea in Sasa lambda is to apply TD lambda prediction methods to just the states or rather than the state action pairs. So Sasa lambda is basically a control algorithm, right? And we do control through Q function, and it involves state as well as action. So they are like saying the reverse thing. Actually, in Sasa lambda, we will apply to state action pairs rather than the states. So this statement is completely false. So I hope you agree with this. So if there is any doubt in any of the questions, you can ask me. Otherwise, I'll move to the next question. So this week, like in practice assignment, there are just 4 questions, also like quite simple ones. So is the TD lambda algorithm with lambda equals to 1 essentially Monte Carlo? Is it true? Like we know, like if lambda is equals to 1, then the return will be Monte Carlo return, because it will be having contribution from all the returns, right? So if we have lambda equals to 1, then TD lambda reduces to Monte Carlo. And if like suppose so this like answer is yes, but like what happens if lambda is equals to 0? If lambda equals to 0, then we will have our usual TD0 algorithm. So this lambda like denotes that value. If it, initially we started off with TD0, then we introduced the general family of these algorithms, TD lambda algorithms. Now question 4. So question 4 is in solving the control problem. Suppose the first action taken is not an optimal action according to the current policy at the start of an episode. Would an update be made corresponding to this action and the subsequent reward received in the Watkins Q lambda algorithm? So in Q lambda, like this is similar to Q learning. So basically, like suppose you are in some state S. First step, you take action A, like whatever like you want to associate this Q value with, you take that action. And from then onwards, like you will reach in S dash, then onwards you will take the action which is like max. So maybe max of A dash overall action, then you will land in S triple dash. And in a similar way, you will again take max. So what the idea here is like the this taking of max starts from the subsequent steps, not the first step. So in first step, you always take action what is prescribed by this Q1. So what you want to estimate. So like will this happen? Yes. So update like it will also be made for this first action also. Okay, so is there any doubt in any of these like 4 questions? If there is, like you can ask me now or in the chat. Otherwise, I will move to next question. So these are like quite simple questions. So now I'll move to next segment basically. So which is the problem solving. So in this, like we will discuss problems which are not part of practice assignment, also not part of assignment. So first question is considering episodic tasks. So this is important. Episodic tasks, and for lambda belongs to 0 to 1. So this basically says lambda is between 0 and 1, but 0 and 1 are not included. So this is like something which is called as open interval. So this means that 0 and 1 are not included, but anything between 0 and 1 is there. And if it was like square braces bracket, then you will include 0 and 1 also. So here they are asking about 0 and 1 excluded. So is it true that the one step return always gets assigned the maximum weight in the lambda return? So this is again key point, like is it does it always happen? And key thing to notice that it is asking for episodic task. So either like you can prove it that it will always happen, or if it doesn't happen, you can give what is called as a counter example. So one counter example is generally sufficient to disprove that statement. So here also like we will do a similar kind of thing. So what is like this return? So it will be like 1 minus lambda, like this will be common. And then you will have GT of 1, right? Then you will have 1 minus lambda will be always multiplied. Then you will have lambda also. And then you will have two-step return, right? And then you will have maybe like if suppose we are considering only just 3 step, then we will have basically like whatever remaining is there. So this combination, like these weights, so should form what is known as convex combination. Convex combination means that all these weights should be like greater than or equal to 0, and they should also sum to 1. So like if suppose we start with a value of lambda equals to 0.7. So here like weight will be 0.3, right? 1 minus lambda. Then 1 minus lambda is 0.3 and lambda is 0.7. So here the weight will be 0.21. So if we have like third term, like the remaining summation from 1, like if we subtract the sum of these two from 1, that weight should be allocated to the third return, three-step return. So basically like this is 0.51. So here the weight will be 0.49. But in this counter example, like we can see that the weight, maximum weight is assigned to the three-step return, not the one-step return. So this basically shows that there it is possible that maybe like the last return can get a higher weight. So this happens in episodic. So like basically like this statement is false. So it's not always true that first one step return will get the highest weight, but this is true for episodic tasks, right? So this is not true basically. So if we have continuous tasks, so if continuous tasks are there, then basically like 1 minus lambda will be always be there, but we are diluting it by lambda every time. So it will keep on reducing. So in that case, you can say like that the first one will get the highest weight. But in episodic tasks, you cannot guarantee that. So the answer is no. Okay, I hope you got this. Okay, there is something in chat. Yeah, okay, fine. So now I'll move to the next question. So this question is regarding TD lambda algorithm. So this is basically which of the following statements are true. And one thing to note is that this is multi-option correct. So more than one option can be correct. So here like lambda is basically the eligibility decay factor. So that is also one. And gamma is the discount factor. So that is also one. If these two have hold, then which of the following statements are true? So if lambda equals to 1, the method behaves like a Monte Carlo method and for an undiscounted task. So one thing to remember is like generally like we have this thing in mind, we think that undiscounted might mean that this gamma is equals to 0, but undiscounted actually refers to gamma is equals to 1. So like this is true, right? Lambda equals to 1 ensures that it will be a Monte Carlo method. TD lambda will behave as a Monte Carlo method and it will behave as a Monte Carlo method for undiscounted task because gamma is equals to 1. So eligibility traces do not decay. Is this also true? Because like basically how do the eligibility traces decay? So we multiply by this factor, right? Lambda and gamma. But since the product of these two term is 1, then like it won't decay. Like if either one of them was like less than 1, then it would have decayed. But now like the eligibility traces cannot decay. So the third option is the value of all states are updated by the TD error in each episode. So key point here is all states. So will it happen that all the states will get updated by the TD error? No, because like only the visited states get updated, right? Because they will have contribution. There might be an MDP, suppose it's like very large MDP, consider like this, and it goes like in a infinitely in all four directions. And if the trajectory sample is like this is your episode. And like these states, other states, they were never visited. So why should the update go to them? So they won't be updated. So this all is making this statement false. And fourth option is that this method is not suitable for continuing tasks. This is also true because for episodic tasks, we can have this discount factor as 1, but for continuous tasks, we cannot have discount factor as 1. The reason is like discount like for continuing tasks, basically this means that there is no end. So it will keep on going and going till infinity. So what happens if suppose we have reward at step 1 as 1, then if our gamma is like 1 here, so there is no decaying of reward. So if second step we get R2 plus R3, and if like similarly we keep on continuing till infinity, then this summation like this is basically representing the value function, like this might go to infinity. So this method is not suitable for continuing tasks. And this is because like gamma is equals to 1. So for episodic tasks, we can afford this gamma equals to 1. So this gamma discounting factor, like it serves two purposes. Like first, it will like determine whether the agent is myopic or it what is the opposite of myopic? So basically like short-sightedness or long-sightedness. So if the agent like prefers like to have like more weight in the later returns also, then he can have a higher gamma. If he wants like just gamma, sometimes the agent can take gamma equals to 0. Then in that case, it will be focusing just on the one step return. So this gamma ensures, so this is like the first major reason why gamma is there. And second reason is like to keep things bounded. Like we do not want to let the things go to infinity. So in order to ensure this, this gamma discounting also helps. So if there is no doubt, I'll move to the next question. Okay. So third question says that assume that you have an MDP with like this. S is the set of all states, and this symbol denotes cardinality of states. So basically, how many number of states are there in that set? And you decide to use a n-step truncated corrected return for the evaluation problem on this MDP. Do you think there is an utility in considering values of n which exceed like this cardinality of states for this problem? So let's denote this by maybe some is- some n is already used. Okay, so let's use this only. So suppose if there is an MDP like this, it has a self loop and it has a terminal state. Okay, so you can see like there are only two states, but like this trajectory can be very long, right? You can like simply keep on visiting this self loop again and again and again and again, and then go there to the terminal state, and then the episode will end. So there is actually utility in considering values of n which can exceed this cardinality of states, because trajectory can be longer than like the number of states, and this usually happens because some of the states in between might be getting visited. So the answer is yes, there is utility in considering values of n which exceed the number of states for this problem. This is a, like just a simple example, where you can take other examples also. If there is no doubt, I'll move to the next question. Okay, so this is also related to the previous question. Which among the following reasons are reasons to support your answer in the previous question? So only values of n lesser than or this cardinality of s should be considered as the number of states is only this. So we saw like this is wrong either way. Like due to previous question, this is wrong. So all implementations with n greater than or s will result in the same evaluation at each stage of the iterative process. Will this happen? No, right? Because like you can like take the last example only. If you keep on repeating in this loop, maybe like suppose 5 times and then 6 times, 7 times, then if suppose we like give a reward of +1 also, and maybe like we can have gamma zero point 0.9. So this will like have different kind of evaluation, right? This +1 extra will come up. So due to this, we cannot say that they will have the same evaluation. So the third option is the length of the each episode may exceed number of states, and hence value of n greater than number of states should be considered. This is true. So this is the reason which we gave in last question also, like the length of the episode may exceed number of states. We saw this example, right? Number of states here is 2, but we can get like episode lengths of like practically anything. We can get infinity also if we keep on like simply looping in this. Okay, and regardless of the number of states, different values of n will always lead to different evaluations and hence cannot be disregarded. So this is also wrong. This cannot be the reason. The issue is with always. Like sometimes it might happen, but not always. So now like this is something which you need to solve. So we have a sequence given. So these are the like sequence of states. Okay, so what is the eligibility trace? E7. So like basically they are asking what is the eligibility of S1 at time step 7. So here like we are starting with 0. Like basically like you can think like S2 to S1, this is first step, then second step here, in between third step, fourth step, fifth step, sixth step, and seventh step. So basically at the end, like what will be the eligibility of state S1? Okay. Given the trace decay parameter lambda, discount rate gamma, and initial value of this eligibility of state S1 as 0, and also accumulating traces are used. So all these things you need to keep in mind. So initially, like you can say like what will be the, maybe like I'll write down S2, S1, S3, then S2 again, then S1, S2, S1, and S6. So initially, like the eligibility of state S1 is 0. Okay. So now like what we will do is we will be like moving to S1. So now S1 is visited. Now, since we are using accumulating traces, so in accumulating traces, what we do is gamma lambda into old value of maybe ET minus 1 of state and plus 1, right? So, but since here like the old value is 0 itself, so this term will go to 0 and it will become 1. Now we move to S3. Now since we have moved to S3, now it will decay, right? So at this step, it will become maybe gamma and lambda. Now S3 to, we are moving to S2. Then again it will decay one more time, and it will decay by this factor, and there will be a plus 1 also, right? Uh, no, not plus 1. Plus 1 will be when it's visited. If visited, otherwise simply gamma lambda into PT minus 1. So since it's not visited, it's simply decays by this factor. Now again, like we go to S2, it will again decay, so it will become gamma square lambda square, right? Now we are moving to this S1. So first like decay gamma cube, lambda cube, and then add this one. Okay. So now this is our eligibility. Now we are moving to S2. Now S2, moving to S2 basically means that it will decay but won't increment. So if we simply multiply with this gamma and lambda. So now gamma 4, lambda 4 plus gamma lambda. So this will be our eligibility, right? Now we are moving to S1. So first, like we are visiting this time, right? So we will first multiply and then add 1 also. So after multiplying, we will get gamma 5, lambda 5 plus gamma square, lambda square, and then we will add this plus 1. Okay. So now we have reached like almost the last penultimate step. So this is S6. Okay, it's S6. Uh, we have written likely S2, S1, S3, S2, S1, S2, S1, S6. Okay. Either way, it's different from S1. It doesn't matter much whether it's S6 or S2. So now we have to decay one more time. That's it. So if we decay one more time, we will get gamma 6 lambda 6 plus gamma cube lambda cube and plus gamma and lambda. Okay, so this is the answer. So now you simply have to match like which is the option. This is definitely not there. 7, we are not getting 7, 6. No, this is also not there. Okay, if we multiply, we will get first term, then here we will get cubes, and here we will get 6. Okay, so this is the answer. And again, like this 7 is not appearing anywhere. So correct eligibility is option C. So I hope like you are able to understand this. Your like these kind of questions might be there in your exams. So you need to follow the step-by-step process and see where it goes. Also, like you can generalize some kind of formula from here. Let's see, like so basically, like what is happening? Eligibility at T of S is given as this formula: K equals to 0 to T gamma lambda T minus K, and this is like some indicator that whether at kth step like the state was this state S or not. Okay, so what I'm going to do is I'm going to like put the values in this formula and see like how it goes. So T in this case is 7, right? Now, and K is the step. At like we are moving from this step to there. T. So let's see, like, so if we open up, it will be, so what are the values of K at which we are having this, right? So we are having this at like K, initially it was 0, then 1, 2, 3, then 4, 1, 4, and 6, right? So we are having K values of K at which this indicator function will be 1 is K is equals to 1, 4, and 6. So remaining, like, this indicator function will say that you didn't visit this state, so you cannot have, so it will have 0. So this summation won't matter. So basically, like, we have to like put the value of, so 7 minus 1. Then this summation will be gamma lambda, and now it will be 7 minus 4 plus gamma lambda 7 minus 6. So from here, like, we got this term, which was actually first in our term. Then we, from here, we will get this cube term. And then from here, we will get this 6 power term. So in this way, like, if you use this simple formula also, like, this is basically derived on intuition, you can get the answer of eligibility traces. But remember, like, this is for accumulating. Okay, so I hope like you got this. Now I'll move to next question. So for the above question, so we are considering the same question. What is the eligibility value if replacing traces are used? So maybe I'll write it down. So S2, S1, S3. We are moving S2, S1, S3, then S2, S1, S2, S1, S2, S1, S2, S1, and in the end it was S6. Okay, so the difference here is like replacing traces. So in accumulating traces, we were like decaying and then adding 1. So in replacing traces, this term will go away. We will simply put it equal to 1. So let's begin. So initially, like, it was 0 as usual. Maybe like I'll ask the person who is unmuted to mute himself. Otherwise, I'll mute. Okay, I have muted. So first visit, like, eligibility will become 1. Now it will start decaying, right? So gamma lambda, again, like gamma lambda square. So now it becomes 1. So again it will decay gamma lambda, and now it will again become 1, and then gamma lambda. So what is the eligibility value if replacing traces are used in the end? Like, it's gamma lambda. This they haven't mentioned, but it's after 7th step. So this is the correct answer. This is wrong, this is wrong, this is also wrong. Okay, so I hope you got this. The difference basically comes because, like, whenever we visit that state, we like put the value to 1. So this kind of structure comes. You visit, then that goes value goes to 1, then at decay, then 1, then decay. And accumulating, it could happen that when you visit, it might go up depending on like whether like the decay is sufficient. It might happen that the decay is sufficient, then it will maybe reach that value only. So in accumulating traces, like, things can go up, but in like replacing traces, like, there is maximum eligibility of 1. You cannot go beyond 1. So I hope you got this. If there is any doubt, you can ask me. Otherwise, like, I'll move to the last question of this section. Okay, then I'll move to the last question. So suppose that in a particular problem, the agent keeps going back to the same state in a loop. Okay, so what is the maximum value that can be taken by the eligibility trace of such a state if we consider accumulating traces with lambda and gamma, these values? So let's consider the general case. So suppose an agent is there, it keeps on going to the same state again and again. And here one more thing is there, that accumulating traces are considered. So like initially you'll start with 0, then like basically you are visiting this term again, this state again and again, maybe call it S. And if you visit the same state again and again, you simply multiply the old eligibility of this state S by gamma lambda and then add one also. So since it was zero, like this factor will go away and it will become one. Now what will happen? Next time you visit, you will get gamma lambda and plus 1, right? Again, you will visit. Now, first, this will multiply with gamma lambda. If you multiply by gamma lambda, then it will become gamma square plus gamma lambda plus 1, right? And again, like if you visit, then first multiply, then add 1. So, gamma cube lambda cube plus gamma square lambda square. This will be gamma lambda plus 1. So you can see like a series is coming up. So basically like these are all positive terms. So if we want the maximum value, then we can sum to infinity. And this is what is known as infinite GP. So maybe someone can tell me what is the formula of infinite sum of an infinite GP. You guys have already seen this before. Okay, either way, like I'll write it. So if the summation is like A is the first term and AR, this is the common ratio, AR squared plus dot till infinity, then it becomes A upon 1 minus R. So in this case, like our first term will be 1 and our common ratio will be gamma lambda. So 1 upon 1 minus gamma lambda. Now we have to like solve for these values. We can solve. This is the general answer, general formula. You can simply put value. So 0.25 into zero point 0.8 will be zero point 0.2. So 1 upon 1 minus zero point 0.2, which is 1 upon zero point 0.8, which goes 10 upon 8. So 10 upon 8 will be 1.25, right? So A is the answer. So in this way, like basic mathematical concepts can always be used of series and sequences. So you need to keep those in mind. It might happen like here, like you had an infinite GP, you might see some other series happening and you might be asked to get the sum. So you need to have those concepts also in mind. Okay, then we are at the end of this section. So now we will move to demo. So as I have told before also, there will be two demos. First will be MLE, MAP, and full Bayesian. And this full Bayesian is basically what is known as Thompson sampling. And then in second demo, we will have Salsa lambda, both accumulating and replacing. Okay, so before like first I'll like explain what is the problem which we are considering. So for first demo, like we will be considering the same problem. There are 3 coins. So like these are, you can say, biased coins. So in unbiased coins, like probability of head and probability of tail both are equal and they are equal to 0.5. But in biased coins, the probability of head and tail need not be 0.5. They will be different. It can be different. Suppose if probability of head is here P1, P2, and P3. So like probability of tail will be 1 minus P1, 1 minus P2, and 1 minus P3. So the aim of the game is to get as many heads as possible. So if we get a head, we will get a reward of +1. If we get a tail, we will get a reward of 0. Okay, so this is the aim of the game. Now your goal is to maximize the number of heads, but the issue here is that these probabilities of heads, they are not known to you. So you don't know. So what are the probabilities of head? So you need to basically explore these coins and then kind of exploit. So you need to balance that exploration and exploitation. So we saw this example using UCB also before. So UCB was like implicitly doing that exploration exploitation for you, but in MLE and MAP, you need to see yourself like how much to explore and how much to exploit. So this like basically forms the bandit problem in which like you can think like there are three arms and you need to decide like which arm to pull, and each arm has a like mean of reward associated with it, but you don't know that mean. So what you can do is you can pull each arm like some number of times and then can have an idea like which one is the best one. So this is the like problem, and maybe I will give you an idea about MLE also. So MLE estimate, maybe I'll discuss this later. First, discuss the beta distribution. So you guys must have heard of normal distribution, or it is also called as Gaussian distribution. So it is parameterized by two parameters, mu and sigma. So mu is the mean and sigma is the standard deviation, right? So similar to like this normal distribution, this beta distribution also has like two parameters, which are alpha and beta. But the difference of this beta distribution from Gaussian distribution is that it is defined in the range of 0 to 1. So this you need to like take care of it. Like it is defined in range 0 to 1 means like here like it won't go beyond 0 on left hand side and beyond 1 on right hand side. So like normal distribution, it can go like this till infinity, right? Plus infinity here, minus infinity. Although like it will shrink very much till there, but it can be unbounded. But here like it is bounded in this range 0 to 1. And these parameters, one more thing to notice that these parameters should be greater than 0. Note that it's not equal to, it's not like greater than or equal to, it's strictly greater than 0. So alpha and beta cannot be 0. This is also a point to note. This we will see in demo also. This is used there. And the mean of this beta distribution is given by alpha upon alpha plus beta. So this is the mean. So you can look into this beta distribution on Wikipedia maybe. Like it involves a lot of complex terms like gamma functions and all. So I'm not making it complicated, but simply we will be using this mean. So I have mentioned this mean. So this mean we will be using in MLE estimate and like map also. So MLE, like we won't assume any distribution. So in map only, like we will be using this mean. And these are like some samples of this beta distribution. Like suppose if it's if alpha and beta both are 1, then it becomes uniform distribution like this. And for different values of alpha and beta, suppose this one red one, like this old one corresponds to like this distribution. Then if you have different alpha 2 and beta 2, then it will become like this. So different values of alpha and beta, these parameters give different type of distribution. So you can try out different parameters values of this distribution. So it was belief about, okay, so the belief about the true mean of this army is represented using beta, number of successes and number of failures. So in our case, like our success will be number of heads and this will be number of tails. So in this way, so if you remember the lectures correctly, like in which like we were basically assume in map estimate, we assume that some kind of distribution is there, and then we have some parameters of that distribution, and consequently, like as we see data, we will kind of update these parameters, and then on the basis of this parameters, like distribution itself will get updated, as you can see here, like different parameters result in different kind of distribution. Then like if we are doing map, then we can simply take the mean of that distribution, or if you are doing full Bayesian, then you can simply sample from that distribution. So in this way, like this works. So I hope like beta distribution is clear to all of you. Although it's like it involves a lot of terms, but you can see the PDF and CDF in any standard probability book or even on Wikipedia. But this is all like what we will need here. Even I shouldn't have mentioned this variance, but either way it's there. Okay then. So I'll start sharing the demos now. So maybe like some of you can confirm if you are able to see my Mozilla. Okay, so now I have shared it. I hope it's visible. So maybe like someone can confirm now. Yeah, okay, it's visible now. So yeah, right. So before directly moving to this, so these are the like usual libraries: random, OS, math, and NumPy. So we are setting the seed also. But number of coins is 3. These are the probabilities. Now, like you already know, we have seen this demo before. So these are the probabilities which we usually take: 0.2 for first coin. These are the probability of heads, right? So second coin is probably unbiased coin. So it's with probability of zero point 0.5. Then third one is the most biased towards head, and we will be doing total number of heads 30. Total number of tosses heads 30. So in MLE estimate, MLE estimate, what happens like eh, so first is maximum likelihood. So as and when we see some data, so we have 3 coins, right? So when we see some data of, suppose we toss this coin, we got maybe head, we got tail maybe next time. Then in this coin we can have head and head. In this coin maybe we can have tail and tail. So on the basis of this, whatever data we have seen, we can have an estimate about like what is the probability distribution which could have generated this data. And it's like maximum likelihood based on maximum likelihood concept. This is from probability. So basically like what this converges to is the mean average. So in this case, like it will be zero point 0.5 for this and 1 for this and 0 for this since it's both tail. But like remember like the real distribution could be different. So this is basically MLE is based on data, what it has actually seen. So if you actually want to converge to the actual distribution which has produced this data, then you need to do this a lot many number of times. Then only you will converge to the actual distribution. In fact, in theory, you need to do this infinite number of times. Then comes the map distribution. So in like MLE, we didn't make some kind of distribution over these means. We were simply using the means itself. But in map maximum a posteriori, what we do is we assume that each of these coins have some distribution, like suppose this distribution. Then what will happen? Like we will like kind of give have some mean of these distributions. Then on the basis of this mean, like we will take some decision like, and this decision will be like which coin to toss. So here also we are taking this decision on the basis of this mean. So suppose we need to take the decision, then we will take coin 2 as the maximum mean 1. So we will toss coin 2 next time. Maybe like next time it might come as tail. Still its probability will be 0.66 something. Then again tail, then it becomes zero point 0.5. So in that case, like we can decide to go to coin 1. In a similar manner, like we will be having the means of these three distribution, and we will like simply use the means of this distribution in map. And as and when like we see more and more data, we will keep on updating these distributions. So maybe suppose if some toss came here, then we will update here. And in similar way, like we can keep on updating. Now, what happens in full Bayesian? Like here, like we are using the means of these distributions. So in our case, if we are using beta distribution, these will be alpha upon alpha plus beta. So we will be using this for decision making, this for deciding between the 3 points. Here, like it's empirical mean, whatever you have seen. Here we will be using mean of the distribution, which we are assuming it to be. And this will be modeled using beta distribution. So this is the mean of the beta distribution, alpha upon alpha plus beta. And then we will be doing full Bayesian, in which what happens, we will simply sample from the, we will assume a beta distribution initially. We will sample, we won't sample just the mean. So we won't be taking decision based on this. We will simply have a distribution. Suppose 3 distributions are there. We will sample from this distribution and see like whichever distribution produces the highest sample. Then we will, on the basis of the sample, we will take that coin. And also like as we see more data, we will keep on updating these distributions also. So this is the like main difference between MLE, map, and full machine. So I think there is something in chat. Okay, so yeah, I hope you got this. So now what I'm going to do is I'm going to show you the demo. So this is like total heads. This basically does not consider like which point. It's simply to track like how many heads have happened till now, and this simply tracks how many tosses. So we are considering 30 tosses here. So outcomes basically like this is a array of array 2D array. So it shows the outcome of each point, and the tosses, this is like not three-dimensional, but an single dimensional array with three elements. So it corresponds, each of the element corresponds to one coin, and it will simply track like how many tosses of each coin we have done. So this will help in calculation of mean, because we will know the number of heads, we will simply divide by the number of tosses of each coin. And these like this array, it's the means of each coin. So this is again a three element array. So initially, like I haven't like mentioned explicitly that it's a three element array or something, but eventually, like when we do it, like you'll see, like it will come out as a three-dimensional array. So here, like we are kind of initializing these. So let's run this. Maybe I'll show you also. So you can see mean. So initially, like the means of all three coins are zero. And maybe I'll show you tosses also. Tosses also zero. And what was the other thing? Outcome. It was outcomes. So this is like for each coin. So it's like you can think 2D array. So like first one corresponds to like which coin, and for each coin we will have like 30. Like some will obviously remain like this hyphen, because at that point like some other coin is getting tossed. But whenever like it gets tossed, we will simply give it head or tail, replace that, and simply count the number of heads or number of tails. So this is outcomes. So one more thing to note in MLE is that you need to like explore each coin like initially. Otherwise, like what happens, suppose you toss one coin. Maybe I'll show in this. There are three coins, one, two, three. You toss this coin and it gave head. And you have initialized the probabilities of heads of all the coins to be zero. So this will have probability one after one toss. Now what will happen if you start being greedy with this mean only? Then you will never explore these 2 points again, because this one will never go down to zero. Regardless, it can coming on tails and tails, but still due to this one, like it will keep on reducing, but it will never go exactly to zero. So in order to ensure that we can like explore whenever we need. So we will do that initially. So this is the basic code. So here nothing is happening, just that we are like randomly sampling a random number between 0 and 1 uniform distribution. And if it's less than probability of point, then we assign outcome of head, because remember this is the probability of head, and we are increasing the total number of heads as 1 plus 1. And then also like we are attaching the outcome for that coin and at which toss of the coin, and also like incrementing the tosses of that coin and total tosses finished. And also like mean will now like we are simply counting this number of heads and divided by total number of tosses of that coin. So let's run this. So as you can see, like we have initialized these means to be zero for. So maybe like in the beginning we can explore each coin once. So it gave head. So this is the problem which I was talking about. If you like start being greedy with this coin, then what will happen? You will never sample these 2 coins, remaining 2 coins again. And you already know from the probabilities that actually coin three and coin three is the best coin. Coin two is the unbiased coin, and coin one is actually the worst. So you might incur a very high regret. So let's do for all the coins once. Two, it gave tail. Three, it gave head. So see, you can see here like coin two got unlucky here. Although like in expectation its probability of head is more, but here like coin one gave the head. So maybe like we can do it twice. So again, one more chance. So see, now it's like 0.5, 0.5 forward. Let's see, 0.3 again. From now on, like you might think that, okay, enough with the exploration. This 0.3 seems promising. Let's try 0.3. Now we start being greedy with this one. Again, it gave 3 heads now. Now 4 heads, 5 heads. So you are happy with the heads. You need to maximize the number of heads and it's giving heads. So carry on with this coin. Now it gave a tail. Still like according to mean, like it is still the best coin. But who knows, like let's try coin two one more time. Maybe it got unlucky. Yeah, coin two gave head. So it's still like now you can move back to coin threes. You can keep being greedy with coin three. It is giving you the more number of heads. See, almost like 9 out of 10 heads. Again, heads and heads. So now it gave tail. Maybe now you want to try out coin two. Let's see, it gave tail. So probably it's 0.5 only. Maybe you want to explore coin one more time. Let's see. It gave head. Let's explore one more time. Head again. So see, MLE estimate is purely based on data. Although we know like the probability of this coin one of head, like probability of head of coin one is much lesser than probability of head of coin two. But the data currently is indicating that coin one is better than coin two. So this is why like MLE estimate requires a lot of data. So although like we are doing for 30 tosses, but in order to be confident, you need to do it like as many times as possible. Theoretically, it should be done like infinite number of times, but practically you can go maybe 10,000 times or something like that. So let's now we have like kind of explored enough. We can simply we start being greedy with respect to coin three because like its mean is quite high. So let's do this. We as long as its mean is above the mean of remaining 2 coins, we will sample coin three only. So 2 more tosses, one more toss left. Okay, so let's see the result. So in the end, like we got like total of 24 heads. So in expectation also, since the probability of coin three was zero 0.8 into 30, it should be 24. So in this case, like our regret is essentially zero. So now there is something in check. Okay, yeah, I hope you got this. Now I'll move to second one. This is maximum a posteriori estimate. And in this, what happens is we will be using beta distribution as discussed in the slides. So for beta distribution, we need two parameters. So the outcomes and tosses parameters is same, and even the means just replaced by mean values name. But remember, like there, the mean was of the data which we were seeing. So it was simply like number of heads upon total number of tosses. But here the mean will be of the beta distribution. So this will be alpha upon alpha plus beta. So this is what will go inside this array. And also these are two other parameters of the beta distribution, successes and failures. So again, like this is also a 3 element array, which will simply count the number of successes of each coin, which in our case is tails, in our case is heads. So basically we want to maximize the number of heads. So this is our success and number of failures will be stored in this array, failures. So it will basically count the number of tails. So again, let's do this. So yeah, so you remember like here, like we are having these mean values from this beta distribution. And I mentioned in the slides also that this is essentially beta of if you have both the parameters as one, then it will be a uniform distribution. So you could have used uniform distribution here also, but since we are using beta, we have like used the parameters which basically make it uniform. And one more thing, like you remember in slides, we saw that we will be using beta distribution And the parameters will be number of successes plus one and number of failures plus one, not just the number of successes and number of failures. And there are like few reasons for this. So you can see like what will happen if like some coins might not get sampled any number of times. So its number of successes and total choices will be zero. So we will get zero upon zero kind of thing. So in theory, like we can deal with it, but in like coding, like these cause implementation issues because there will be division by zero. So maybe like Python might not handle it. Let's see, like if I do zero by zero, what it says. See, it gave an error, division by zero. So these kind of things, implementation issues are always there. And also fairness, as we will see in the demo. So although initially like we are having uniform kind of means for all three coins, but if we don't sample a coin, we don't know its mean, right? So it will, as you will see in demo, like it will become zero point 0.5 as soon as possible. And this is like reasonable also because uh, it is like successes plus one will be our alpha, and up in denominator it will be successes plus one and failures plus one. So successes and failures both are zero, then it will be essentially 1/2, so zero point 0.5. So this kind of ensures fairness also, that we don't know the mean, so it's better like keep it unbiased coin. It could be like anywhere like beyond, like anywhere on the left hand side of 0 0.5, also anywhere on the right hand side of 0 0.5 also, but 0 0.5 like we will keep it. So this kind of ensures fairness. Also third reason is that beta 1 comma 1, this I have already mentioned, it is the uniform distribution, and beta 0 0 is not defined. So maybe like you can google some beta distribution plotters and you can put these values 0 and 0 and see the graph. It's not defined, it won't come. And also like you might think that this plus one might change things. Like we are not actually sampling from the distribution which we should have, but it won't because like although like here we are doing for just 30 number of tosses, but in practice you will be doing this maybe for 10,000 or lot many number of steps. So number of successes, even if it's 5,000 or 5,001, it doesn't really matter, right? So let's do the map one. So before doing the map one, so here you can see like this mean values, like basically like this is the main step. So here we are using this mean of the beta distribution, which is like this is our alpha. Our alpha we took as successes of coin plus one and divided by alpha plus beta. So alpha is this and beta is failures of coin plus one. So this we are like maintaining for all the 3 coins, and accordingly like we will take decision. So as you can see here, like we have assumed some distribution and we will be taking decision on the basis of mean of this distribution, but these distribution will keep on getting updated as we see more and more data. In full vision, like we won't be using mean, but we will be simply drawing sample from this distribution and we will do that. So now let's begin with this one. So as you can see, like we uniformly use that distribution to initialize the means. So here it like kind of gave the highest to 0.64. So 0.64 to coin 2. So let's do coin 2. So it gave head, now it became 0.66. So remember, like these are not the means of like MLE kind of means. These are means of beta distribution. So it's not one. That's why. So basically, like number of successes plus one will be two, and in divide denominator you will have number of tosses, which is one, and but plus one of success also plus one of failure also. So it will be 2 by 3. So let's do coin 2. So remember the point I mentioned that if you have not tossed any coin, then its mean will become zero point 0.5. So this has also happened. So we didn't sample this coin 1 and coin 3, so their means are zero point 0.5 now. So as of now, like based on data, like we will sample coin 2. Let's see. Coin 2 again head. So as soon as like basically our aim is to get as many heads as possible. So although like we know that coin 3 is the best one, but if we are getting heads from the, we know that coin 3 is the best coin, but if we are getting heads from coin 2, we will take it. So we follow coin 2. Now it gave head again, so its value is increasing mean. Now again it gave head, again head. So this might happen even though it's 0.5, but these kind of things can happen. Now it gives tail, but still it's still the best coin. So we sample coin 2. Let's see. So now 2 tails. So now 3 tails. Now we are slightly worried about this coin. Now again head. So now you can see like the importance of exploration. So these two methods, MLE and map, these two like they don't explicitly like they don't implicitly do this exploration exploitation thing, which Thompson sampling does. So we will see this, but now maybe you want to explore coin 1 and coin 3 because you haven't sampled them. So let's do that. So maybe 1, it gave tail, maybe 3 now, it gave tail. Maybe one time more. So it gave head, then let's do for coin 3, gave head. Still like this didn't change anything. It was like it remains 0.5. So let's go with coin 2. Coin 2 keeps on getting more and more number of tails now. Reduce to 0.57. Again tail 0.53. Now we are again worried. Let's do one more time. Oh, it's process left is 20. Okay. Let's do coin 2 one more time. So now you can see here the difference comes. Like this coin 2 is now essentially like half the number of heads and half the number of tails. So now we can go to coin 3. Coin 3. See, it gave head. Now it gave head again. So although like in hindsight we know that coin 3 is the best coin, but in order to reach that stage, we took a like lot of tosses. Like just 8 tosses are remaining. So maybe from now like we can keep on doing this. Coin 3. Now coin 3 is also reducing due to tails, but again it's back. 3 head. So 2 tosses left. So let's see how many heads we got in total. So in total we got 19 heads. So this is the like kind of issue if we don't do full Bayesian kind of thing, because if we are simply using the means might be misleading. Even in this case also like MLE, like we initially did some exploration that helped us. But if like maybe like initially if coin 1 got the head on the first attempt itself, and it would have been difficult if we didn't do that exploration of coin 2 and coin 3, we would have simply continued with this coin 1. And in the end, like we would have like been suboptimal. So now we will see the full Bayesian approach, which is essentially the Thompson sampling. So again, similar to the previous one, like these are the like parameters, but here like instead of mean values, we will be having beta values, and this is basically samples from each of the distributions. So remember, like in map, we were like simply using the alpha upon alpha plus beta mean, but here we will be actually drawing sample from the distribution and see like what sample it gives, and whichever like gives the highest sample, so we will take that coin. And this is like if we do a large number of times, this actually converges to the true expectation also. So it makes sense if suppose the distribution of a mean is that like the distribution is centered around zero point 0.9, and if our distribution is centered around zero point 0.1, then it's likely that the samples drawn from the distribution centered at zero point 0.9 will be higher than the samples drawn from distribution centered at zero point 0.1. Maybe I'll show you this one. Suppose the distribution is there. So this is 0.1 line and this is zero point 0.9. So it has, although like these are normal distributions, so these can go till infinity. So even if we consider beta distribution, even if it's restricted with 0 and 1, so you can see like how unlucky it has to be to get a sample here, right? And it has to be extremely lucky to get a sample here. So most probably it will be in some range here and here. So in this way, like that expectation is there. So this Thompson sampling implicitly enforces exploration. So like in the like previous two methods, we have to explore on our own, but now in this Thompson sampling, we don't have to do exploration. It will implicitly do it for us. So let's see how it does it. So here you can see like it is actually sampling from the beta distribution whose parameters are these alpha and beta. So it is not using like the means, but actual samples from the distribution. So let's go for point one. Okay, so coin one again, coin one. See, as soon as it gave tail, the next sample became 0.6 and we moved to coin three. Again, coin three gave head, so its sample is closer to 1. 3. Now it wants us to explore coin two. Let's do coin two. Coin two also gave head, but now the sample one is best for coin two. Let's do one more time, coin two. So as long as like we are getting the heads, we don't mind pulling that coin. So let's pull coin two again. Let's see, it gave tail, so it varies now. Now we will toss coin three. Okay, it is giving heads, but you remember like now coin one got extremely lucky. Like although its distribution is centered around zero point 0.5, this is around 0.66 and this could be around point exactly 1 near 1. So now coin 1 got lucky, so let's sample it once. But if it gets tails, then its distribution will diminish. Now we move to coin 2. So these are samples. So there might be some luck factor here and there, but eventually if you do a very large number of times, then that luck kind of averages out. So now we go to coin 3. So maybe by now you can think like it might have learned enough of about the distributions. So let's do for coin 3 again. See, now we are getting higher values for coin 3 because it is giving us the heights. But now it wants, now coin 2, like it got a lucky sample. So we go to coin 2, but it gave tail. So it's like sample videos. Now coin 3 gave 0.95. So we go to coin 3. Now again coin 3. Now 5843. Still coin 3. Coin 3. Coin 3. See how many tosses are left? 10 tosses. Now coin 2 got lucky. Let's do coin 2 once. Again tail. So coin 3, coin 276 is the best. Let's do coin 2. It gave tail. So coin 2 has actually given us 4 tails and 3 heads. More number of tails. So it is like kind of bad coin. So coin 3 is getting recommended now more and more. Again, like somehow coin 2 keeps on getting lucky. So now coin 3 back to coin 3 still tail. Like it gave 5 tails. Coin 3. Last toss. Again coin 2. So now we can see how many tosses, like we got like 20. So like if we do like a very large number of times, maybe 50,000 or something, then you will see this Thompson sampling will perform the best among these methods, because the main advantage of Thompson sampling is that you don't have to do the exploration yourself. That's algorithm itself is doing the exploration exploitation trade-off for you. So you don't have to do it explicitly. So it is happening implicitly in Thompson sampling. So I hope like this is clear to all of you. Maybe I'll check chat once. So there is nothing in chat. So yeah, okay. Now, what I will do is like I'll list some of the further experiments which you guys can try out. So, although like we took the usual means of zero point 0.2, zero point 0.5, and zero point 0.8, you can play around with these means. You can have like closer means like zero point 0.4, zero point 0.5, zero point 0.6, and see like there what happens. And you can try out different number of coins. We had like 3 coins. You can try out more coins or less coins, also 2 coins maybe. You can try out 5 6 coins also and try out different number of tosses. So basically like here the thing is like the more data we see, the better results we get, better estimates we get. So you can, although like due to like this time limit of this lecture being 2 hours, we are restricted to 30 tosses, but you can go beyond 30. So I'll be sharing these demo files with you so you can run those. And like since these are notebooks, you can simply load in Collab and run these. You don't have to install anything. And you can try out different distributions also. So different distributions, what I mean is like we use beta distribution, but you can try out Gaussian distribution or whatever distribution. But there you'll have to figure out how to update the parameters. So Gaussian distribution has mu and sigma. You'll have to figure out if you see some like head, then maybe like you'll need to update the mean and sigma in such a way that the updated distribution represents the current data in a better manner. So you need to take care of those caveats, but you can try out different distributions. Beta, like beta is the one which we have done. There are many probability distributions, so you can try out those. So maybe like I'll download this while we sharing this. Now we'll be moving to second demo of today, which is SASA lambda. So you remember this SASA lambda algorithm. So it's a like control algorithm, TD control algorithm, and we are basically decaying the eligibility by this lambda. So here like the problem which we will be considering is this frozen lake. I'll maybe go to the link first. So these are like environments from provided by this Zim. So what happens in this game is like there is a like 4 by 4 grid, and basically like there are 16 states for us. Like you can represent this as 0 0, this as 3 3, and in this way x and y coordinate can represent all the states. So there are 16 states, and the actions which you can do is up, down, left, right. And there are few like these um, holes in which you can fall. If you fall, then the episode ends and you get maybe negative. Let's see what is the reward here. So reward is okay. So +1 for goal. Even if you fall in the hole, it's 0. So that's not the point. So the only reward which you will get is if you reach the goal. Otherwise, you will be getting 0, even if you fall. So there is no negative reward for like falling in the hole. But you can try out these rewards, you can change. And action space is discrete with 4 actions. Observation space. Observation space basically represents the state space. So that is also 16 because there are like 16 cells. So this is the basic description of this problem. And the episode ends like when the player moves into a hole or player reaches the goal also. So basically like this is like 4 by 4, but you can change those also. So here like they have given this in general format, like this would be the location. So if you are using maybe 10 by 10, then it would be 9 9 coordinate. And you can have a like time limit kind of thing also, because like if when you move to, so there might be a possibility that agent is simply roaming around, neither falling in the hole nor reaching this. It is simply doing a cycle. So you can have timeout kind of termination also, that maybe like if you don't terminate after 1,000 steps, then we will manually terminate that episode. So all those kind of, so this is like just one of the environments. So there are many environments in this gym available you can try out. So people use this to test their reinforcement learning algorithms, these environments. So this is like imported here, imported gym. Then we have NumPy, randoms, matplotlib for plotting, and warnings. So this is the epsilon greedy one. So remember, like we need to follow an epsilon greedy policy because we need to ensure exploration. So what is going into this function is state. So the current state. for which you want the action. So this function will basically return the action. It could be an exploratory action or a greedy action. So it is basically like taking the max over the q values corresponding to that state. So this q value table is also coming in this function, and epsilon is the exploration factor. So basically what we are doing is from this Q value table, first we are extracting the Q values corresponding to that state. So for each action, there will be one value. And we are taking that max over that values, and number of actions will be length of these Q values. And we are greedy actions. So there might be more than one actions which might have the max value, right? So this greedy action is storing the indices of those actions which have the max value. And again, like this epsilon is the exploration factor. So if we throw a random number and it turns out to be less than epsilon, then we have to explore. So in that case, we will simply randomly choose any of the action. Like this range will indicate like complete range of the action, and we can choose any one of them. And if we are like not being greedy, we want to exploit, then we will choose the one of these greedy actions. So you can choose any one of them since all of them will map to the same max values. So there might be possibility that more than one action can lead to like maximum Q value. So again, this is the environment. So this is where like we are calling that environment. These are the hyperparameters. So episodes like we will be doing for 10,000 episodes. You can change these later. And gamma is the discount factor, which is 1. So remember, like this is an episodic task. So for episodic task, we can have gamma equal to 1. You can change these later and try. And alpha is the learning rate. So remember that TD update equation in which it was old estimate plus, so new estimate equals old estimate plus alpha times. So that alpha is there, alpha times TD error. So this is the learning rate. It's 0.1. Again, you can change this later. And epsilon is the exploration factor, which is getting passed here. So this we have taken as 1 initially. But the thing is like we are decaying it. So you can keep it constant also, but if you want to take it constant, then don't take it 1, maybe take it 0.1 or something. But since we are decaying it, so initially we want to explore, but eventually like we will be multiplying this epsilon by this number, and it will keep on decaying. So gradually like we will reach a stage where this epsilon becomes close to 0, and we will be simply exploiting. But initially we will be exploring more and more. So also eligibility decay. So lambda. So lambda is 0.3. So I haven't used the variable lambda because lambda is a like reserved keyword here. So if I use lambda, I cannot use it. It is reserved for something else. So you need to be careful of. There are some lambda functions. So it is reserved for them. So like first we will be seeing accumulating traces. So in accumulating traces, so number of states, you can get this from the environment. So this will return the number of states and number of actions also. Then basically like we are initializing this Q value table. So this will be a table. So for each state action pair, we will be having a 0 initially. But this table will keep on getting updated as in when we see more and more data. And returns is just an array to store the returns. So next, next week, like we will be seeing function approximation techniques. So what happens there is, so you see this Q table. So this is essentially dimension of number of states into number of actions. But if number of states and number of actions are very large, sometimes even infinite, then like we cannot have this big tables in our like whatever local repo or wherever we want to store. So in those cases, we will use function approximation. So those are the like topics for next week. So here you can get the motivation, like if like number of states, even if it's between 0 and 1, if it's taking real values, then there are infinite real values between 0 and 1. And maybe number of actions, suppose if you are driving a car, so action is like by how much degree you should steer the wheel. So it's a real number, right? Even though you can discretize it like 1 to in integer degrees, but essentially it's a real number. Or maybe something like how much pressure you should put on something. So all those actions can be continuous. So in those cases, this table becomes very large and it becomes infeasible to maintain such tables. Then we use neural networks there for function approximation. And neural networks is just one of the function approximation techniques. There are other function approximation techniques, also tile coding and linear function approximation. So those all will be discussed in next class. So this we have basically initialized. Now this is the main code. So for episode and range of episodes, so like here, like we are traversing over all the episodes. So when the episode ends, like we reset the state, have a start state, and this like epsilon, like every episode we are decaying this epsilon, right? And we are basically getting this action. So we have a start state here by this reset function. So we are passing this state into this epsilon greedy function. It will return some state, some action for us. And initially, like since we are like beginning with this epsilon one, then initially it will be simply exploring, but eventually it will exploit. So we will get a exploratory action here. And also like we have passed the Q table. Initially it's zero, so essentially like all the action will have a higher value, highest value. So it's either way, it's random. So it's exploring only in the beginning. And this is the reward ID. So it is empty. So it will be storing the rewards. And this is the eligibility trace. Again, like you remember, like in control, we need to like maintain eligibility for each state action pair. So again, this is a table of like number of states into number of actions. So initially we will have like zero eligibility for all the state action pairs. So while true. So in while we don't have a condition because we don't know how long the episodes could be, right? So the length of the episodes is not something we have in control. Some episodes might terminate very quickly, some might go on till infinity also, but some might like if we don't want things to go on and on, we can set a limit of like this is the maximum number of steps in an episode. So if it reaches that number, then it will terminate. So this done vector, done variable, like kind of returns this. So basically, like you remember, this is accumulating traces. So in accumulating traces, what happens? First, if we are for that state action pair, first we will either way like for all the state action pair, whether regardless whether we visit or we don't visit, we need to decay it, right? Yes, this was. So in accumulating traces, our like current trace. So this will be for state action pair now, since we are doing control. So it was essentially like either way, like you are decaying by this gamma lambda factor. And if the state viewer, like this will be old estimate. So you can think like ET minus one. And if we are visiting, then it will be having a plus one. Otherwise, like it will simply remain this. So either way, like this multiplication by gamma lambda is happening in both ways. So we are doing this. So eligibility decay. Eligibility decay is the like variable name for lambda, which we couldn't use. So you keep this in mind. So this is essentially the lambda. This is the gamma, and this is the eligibility complete. So numpy ensures that every element gets multiplied since this is scalar multiplication. And for the state action pair, which we actually used, for that it will be incrementing one. For others, it will be simply decay. So this is what accommodating traces does. So in replacing traces, what happens instead of this plus equal, you will simply have equal. So it will simply put it as one. Now what we are doing is we are taking that action in the environment and then environment will return us the next state and the reward. Also, it returns something called done if the episode is terminated. Now, based on this new state, we will take new action. Remember SARSA? SARSA is like on policy. So SARSA. So we need this next action also in able to compute the update for SARSA. So state action reward this we already have. We got the next state, but we also need this next action also. So this is the essence of SARSA. That's why like we are using this next action also. So this will be used in calculation and we are simply appending the reward in this reward array and then we will be having this delta. So delta is our TD error, right? So reward plus gamma times like the new estimate minus the old estimate, right? So this entire thing is the new estimate, reward plus gamma times Q value of new state, new action. So here like that new action was needed in SASA. So this is the usual TD error. Then we are updating this. Like this is the TD update equation, but remember like here we are also multiplying by eligibility. So Q is equals to new Q. So this basically stores new Q is equals to old Q plus alpha into delta. Delta is the TD error. And here like we are also multiplying by eligibility so that it only updates those which have eligibility, some like non-zero eligibility. So it will update those only. And then like we are simply changing the state and action. So we are moving to the next action and next state. And in this way like this will continue. So this is like while loop is over the episode, like within the episode, like within the like on the steps, and this for loop is like within across the episodes. So maybe in episode 1 you might have 10 steps, then in episode 2 you might have 20 steps. So while loop is taking care of that how many number of steps, and this for loop is taking care of how many episodes. So we have set the number of episodes to be 10,000. So like here, like if we have reached the terminal state, then we will break out and a new episode will start. Then we are also calculating the return for plotting purposes. We will see some plots later. So basically like length of the reward, this will be like, since we are doing like this TD lambda kind of algorithms, so we need this T step return also. So we are computing this. So this is happening in a recursive manner, but you can see like how it will happen. So initially like our G is 0. So we are multiplying, we are having like, we are like taking it in the reverse manner. So maybe I'll give you an example. So we have initial value of G is 0, right? Now let's see what is happening in this. So we have G T minus 1. Suppose if we are doing for 10 step, so we can take T equals to 9. And this is because like in Python, like this indexing is 0 to 9. So we have this T equals to 9. Now what is happening here is like while T is greater than or equal to 0. So we are gradually decreasing to 0. Here that decrease is happening. And while that decrease happens, what we are doing is we are taking the reward at Th step and adding it to gamma and G. So initially it will be 0. Now what will happen? We will have reward sum maybe 9th plus gamma times this 0. So we are basically having this of 9. Now next time what will happen? We will have reward of 8, but it will multiply by gamma into this thing. So in this way you can see that gamma, this is 0, essentially it got multiplied by 0. So gamma will come for R9. Now since this process will keep on repeating, so now it will be R7 plus gamma times R8, and it will be gamma square. So in this way, like those gammas will adjust, because in the end, like we will need more gammas for the last one. So every time like one extra gamma is getting multiplied. So this is a way to calculate the return. So this is simply for plotting purposes. Also like we are doing some averaging because this is to avoid congestion. So since there are like 10,000 episodes and there will be a lot of values for these 10,000 episodes. And if we are like trying to plot all these 10,000 in this small like graph, then maybe I'll show you. If I simply plot the returns, what happens is this thing. You don't see anything. Okay, so what is the issue? Okay, this is not defined. Maybe I'll run this first. Mhm. Negative dimensions are not allowed. Did we run this? Oh, we didn't run this. First, I need to run this. Episodes is also not defined. Okay, so we haven't run this also. First, I need to run this, then this. And this X1 greedy is also not different. We haven't run anything. Maybe I'll run all. So now this is one, this is one. Everything is running. So since we are like doing for 10,000 episodes, like it's taking some time, but maybe like let's give it some time, 2-3 seconds. It will take more. There's something in chat. Yeah, welcome. Okay, so maybe I should have run it in the beginning. Either way, like let's see. It took 27 seconds. So it's completed. Now this is also completed. So see, this is what is happening. Like you cannot do without this. So we are doing this averaging kind of thing over 100 windows. So for each like 0 to 100, it will plot just one value. So that way, like we can see the graph better. Maybe I'll undo this. And now we can see some graphs. See, this is the graph which we got. This is for accumulating traces. So these are the like the episodes. So just might I'll run it again. There is some issue. Meanwhile, I'll show you replacing traces. So it's also similar to this. Only change happens here. So there, like we were doing this plus equal to one, but here we are doing simply equal to one. So now, yeah. So now it's perfect. So as you can see with accumulating traces, we are like initial episodes, we are not getting that good return, but as and when like we see more and more data, we are getting the rewards perfectly. And eventually, like maybe at the end of 10,000 episodes, we are getting reward of 0.8 on average. So if you do maybe more number of episodes, it would have reached even one because it would reach the so 0.8 basically means that 80% of the times it's reaching this like goal state. Remaining 20% times it is falling in hole or maybe episode terminates without it reaching the goal. It gets a reward of zero in those episodes. So eventually, like if you do for a long number of episodes, it will go there closer to one. So similarly, like we have replacing traces also. So almost the same code, but the only difference is here, instead of doing plus equal to one, we are doing straight equal to one. So this will ensure that it never goes beyond one. And again, the similar kind of averaging. But here we can see like in replacing traces, what has happened is like it has reached a maximum reward of 0.14 only. And so this basically means that also like you can see like this took how much time? This took 15 seconds replacing traces and accumulating traces took 27 seconds. So you can see like accumulating traces since we are updating we are having more eligibility. So it's like not decaying very quickly. So we have to make more number of updates. So it's taking more time. But in replacing traces, since we reset it to one, so you remember in accumulating traces, it can go beyond one also. So due to that eligibility, like it's very like it doesn't decay very fast. So but in this replacing traces, it is limited to one only. So in that way, like we have to make less number of updates. So it took only 15 seconds. But again, like the trade-off is here this that this is for like it's not converging, right? It's stuck at 0.14 only. So one more reason could be like there are a lot of hyperparameters. So you might have to do hyperparameter tuning or simply increase the number of episodes. So maybe like you remember like it took 27 seconds for accumulating phases. So it has made more number of updates, but it took less time for this because it has made less number of updates. So maybe if it also makes that similar number of updates which accumulating traces has made by increasing the number of episodes, it might also get good reward. So these are the like further experiments which you can try. So also like there are a lot of hyperparameters in these 3D lambda algorithms. So you need to like strike the perfect combination. So you can tweak these hyperparameters. Like gamma is the discount factor. So you can like in our experiments we had gamma equal to one. You can have like 0.5 to ensure that the agent has some feeling of urgency to reach the goal state. Otherwise, like the +1 which it is getting for reaching goal state, in our case, it's not getting diluted, but in this case, it will get diluted. So it will try to reach as soon as possible. Then you can try learning rate also. We have 0.1 epsilon, like this is the decay factor. So this is the exploration factor. So you can decay it in a different manner. We decayed it by 0.999. So you can start off with some other value than one, and then you can have different value of lambda also. We had, I think, 0.3. Where is lambda? So eligibility decay, yeah, 0.3. Then you can run for more number of episodes, especially for this one. So in like we have limit like already it's 740. So you can run for more number of episodes. Then you can implement aggressive version of Sasa Lambda in which like only the update is made for that state action pair. For remaining, it becomes zero. For like the same state but other actions, it becomes zero. So that aggressive version you can try. Then you can try dash traces also, but this will introduce one more hyperparameter beta. So you need to handle that also. Then you can try Watkins Q lambda also, but again, this was mentioned in lecture also that it might not work very well in practice, but theoretically it's there. And you can try different environments. This is like frozen lake is one of them. You can try different environments. Even within this, you can try different dimensions and all. So, okay, so that was it for the demo side. So now I'll quickly move to the like this assignment. I'll start sharing this screen. So maybe someone can confirm if you are able to see the slides again. Okay, then you are able to see the slides. Now I'll like quickly go through these questions for assignment. So again, like this one is asking which of the following is the correct n step truncated return. So n step. So this is not that, right? And is this the one? Plus gamma is decaying perfectly. And ST plus one. Yeah. Like, is this the one? Right. Yeah, this is the one, right? So either way, like in assignments, I'm not supposed to give you the answer, but you need to think like whether the gammas are properly there. So here gamma is starting from the first revolve is 12, but gamma, like like it should start from the second one. So you can have that mind. So either way, like you can get the answer from this. Now I'll move to the next question. So which of the following is the correct way to implement replacing traces? So in replacing traces, we make it one if we visit that state, otherwise we simply decay. So what is happening? We are making it one if that state is not visited. This is wrong, right? This is reverse of replacing traces. So these two terms are essentially switched up. And we are decaying and plus one. This is accommodating, right? This is also wrong. And this is accumulating, but like kind of these two terms are switched out. So this is also wrong. And this is the replacement process, right? So this is simply from the, if you have watched the lectures, you can get the answer for this. Like if you are visiting that state at time step t, then the eligibility will become one. Otherwise, you simply take it eligibility. So now the third question is an assertion vision kind of question, which asks that TD1 is a way of implementing Monte Carlo with eligibility traces, extends Monte Carlo for continuing tasks. Yeah, like this is true, right? Because we remember like if we have TD1 basically means lambda equals to. So lambda equals to 1 corresponds to Monte Carlo and lambda equals to 0 corresponds to TD0. So this is like assertion is true. TD1 is a way of implementing Monte Carlo with eligibility traces. And it extends Monte Carlo algorithm for continuing tasks because like Monte Carlo, like essentially it's offline. We were making updates at the end, but now we can do in an online fashion also through this TD lambda version and like we can do for continuing tasks also in this online version. So assertion is true. So this option is gone. Now, TD1 implemented with eligibility traces is an offline algorithm. So this I have already mentioned what it is. It has to be online, right? Otherwise, like this default Monte Carlo was already offline. So we use this TD lambda concept to make it online so that we can use it for continuing tasks. So this says it's offline. So that is not true, right? Now, if there is any doubt, you can ask me. Otherwise, like I'll move to the next question. Okay, then either way, like I'll move to question 4. So again, another assertion reason kind of question. So it says that it is not necessary for a behavior policy of an off policy method to have non-zero probability of selecting all action. So let's like have this behavior policy as mu and estimation policy as pi. So in off policy, what we do is important sampling, right? You might have remembered this from last lecture. So we were having this kind of ratio, suppose pi of selecting some action is not necessary for the behavior to have. Okay. Action. So this is the ratio. Like we basically wanted to avoid some kind of this thing 2/0. Theoretically, we want to avoid this kind of thing. But like, is it necessary to have always like non-zero probability of selecting all actions? So this is corresponding to behavior policy. So behavior policy is new denominator. So does denominator always have to be zero? This you might remember from like some of the last lecture. At upon zero kind of situation is allowed theoretically because like those ratios were getting cut. So 0/0 is fine. So it is not necessary always, but it is necessary only if like the numerator is also non-zero. But if it's zero, then we are fine with it. So this is like what is this? This is true. It is not necessary, right? And if the probability of certain actions in estimation policy is zero, then the probability of selecting actions in behavior policy can be zero. So this is basically saying 0/0 kind of thing is allowed, and it would not cause any trouble in the learning procedure. So is this like this is true, but you need to figure out whether this is the correct explanation of this. So based on that, you can get the answer. But I think like you already know what is the answer. So both are true. Now, if there is no doubt, I'll move to question number 5. Question number 5, again like true false kind of thing. This is considering episodic tasks and for lambda 0 to 1, one step return always gets assigned with maximum weight of the lambda return. So episodic, I think like this question we have already seen in problem solving. It was exactly this question. So you can get the answer from there. Either way, like it is false, right? You know this from there also because like we saw an example in which like it was I think 0.3, 0.21 counter example and remaining was 0.49, right? So like it was getting like more weight to the three-step return, not the first step return. So that counter example applies here also. This is essentially the same question but reframed in a different manner. So again, an assertion reason kind of question. So it says it is possible to use the forward view of eligibility traces with target for updates before the end of an episode. So eligibility traces. So can we do this before the end of an episode? This is false, right? Because what is this lambda kind of return? So it is like essentially maybe if we use some weights, let's denote it by 1 gt of 1 plus w2 gt of 2 and so on, right? Maybe wt gt of t, and these weights like will be all greater than equal to 0 and summing to 1. So this is the weights, but the point is like you might remember this equation also. It was some 1 minus lambda, then lambda was getting multiplied, and eventually like in for episodic task you need like whatever sum is remaining, like you have that term here. But the point is like you need the last like this step return also. So you cannot make the update before the end of an episode, right? So you, although like you might have computed these previous returns, but for this return you need to wait till the end of the episode. We cannot use the forward view for of eligibility traces to make updates before the end of an episode. So this is false. So essentially, like if assertion is false, there is only one option remaining. But either way, like we see if the reason also. GT lambda is the weighted average of the terms of the form this, where is computable after a finite number of steps, making also computable after the finite number of steps in all the cases. So, but like here, like this won't happen for continuous tasks, right? It is mentioning that you can compute this return in a finite number of steps. But if the episode is not terminating, like if you are considering continuous tasks, you remember there were two variants of this in which like we were having this 1 minus lambda for first return, and then 1 minus lambda into lambda for second return, and it kept on going. It never terminated. So those cases, we cannot say that this return is computable after finite number of steps of I. So and this makes this computable also. So this happens if the task is episodic, then you can say that at the length of the episode you can calculate this, but for continuous task you cannot say this. So this is also false. So again, like although like we would have got the answer from the assertion only, but either way, like both are false. So now we move to question 7. Question 7 says, which of the following is a way to use replacing traces in Salsa lambda such that we only update the estimate for the action A taken in state S in that variable. So Salsa lambda, like we have already seen the code. I think like you should be able to do this. So this you can see like it's actually accumulating. We don't do plus one in replacing traces. So it's asking for replacing traces. And does it become one? Yeah, this seems correct, but something is missing here, right? You know that something. That something is action A. There's not eligibility for a state, but state action pair. So this will also be wrong. And again, like you can see this, what is this? This is something called, remember, aggressive form of Casalanda. So this I have already told you that you can try to implement this. In this, what happens is like if the state is visited, but like you take some other action, and for those action, instead of decaying, you make it zero. In normal like Salsa lambda, you are decaying for them also. So also I think there is a typo everywhere. So S comma 8 should be S comma 8. But either way, like this is aggressive form of Salsa lambda. This is not replacing traces. It's accumulating here also. So this is also wrong. So there is only one option remaining. Now we move to question 8. So if there is any doubt, you can ask me. Like I might be moving quickly, but like I think like the questions are simple enough. So let's go to question 8 now. So question 8 says that it's again an assertion region. So too many assertion region in the assignment. So essentially, like there are no solving kind of questions. So you need to have this when using an epsilon greedy exploration strategy and Watkins Q lambda, the epsilon must be kept low. Yeah, because like you remember what was happening in Watkins Q lambda. So you remember this diagram in which we were moving from some state S to S dash, and from then onwards you were taking max over those actions, right? And moving to maybe state and keeping on max. But at some point, if you do an exploratory action, and if this epsilon value is high, then this will have these explore. Suppose epsilon is maybe zero point 0.5 itself. Then with half probability, it might happen that the next action is not the greedy action, but the exploratory action. So these trajectories will become very slow, very small, right? So essentially what we want is it to be longer, but that won't happen. So this statement is true. We should keep the epsilon as low as possible. This is true. Now, okay, so the reason they have given is quizzes will become too short if a high value of epsilon is used, negating many of the advantages of using eligibility quizzes. So essentially, this is the like reason, right? So this reason is also true, but you need to figure out whether this explanation is the correct explanation or not. You know, like whether it's not or it's so it is essentially because like this is what we got here. So now the question number 9. So what does question number 9 say? Consider the current state in S and the action recommended by policy A1 is taken. Okay. The possible reason behind setting is R. So, okay. So essentially this concerns the aggressive form of Sasa lambda. So basically it is asking what is the possible reason that you assign this to be 0, like for the other actions. Uh, Okay, this can be for the non-aggressive version also. It's essentially the pair only. So even if like why you are like setting it to be 0, because like reward obtained by taking A1 in S should not be attributed to the action other than A1. This is like kind of correct intuition. So you remember this example, right? There was a self loop and there was a terminal state and we were moving. So this contribution, if there was reward plus one, then this contribution should not be assigned to this action, right? So in that way, like we were assigning this 0. So this is true. And the second is it assumed that the time steps between reaching S are large enough to decay the eligibility traces to 0. But did we make any of this assumption that the time steps between reaching S are large enough to decay the eligibility trace to 0? So maybe if the decay rate is quite low, like basically it means like suppose if we have lambda is equals to zero point 0.1 something, so then it will decay very quickly. So it might decay to 0, but we don't, we never made this kind of assumption, right? So this is not. And because we can have any value of lambda, right? We can have lambda 0 to 1. So for lower values, it might decay enough to make it 0, but it's not possible for all values of lambda. So essentially this won't hold always. So which of the following are correct reasons you can get this from here. So now the last question of the assignment, it says in off policy TD lambda, okay, which of the following is a correct way to update eligibility trace? Okay, so if pi is the policy whose, okay, and mu is the, this is the row factor. So pi is the, so this they have given, this is the like importance factor. So if you remember from the lectures, like we were basically, what is the issue with this one? So the issue is like this row, it should have been like multiplied like to the entire term, not just like the first term as it is happening here. So this is long, but is this fixing it? This is fixing it, right? Otherwise, like we are simply decaying. If we are visiting that state, and we are like multiplying by this important factor also. So this is true. And since it's single option correct, it will make others false. Either way we see it, like this row is missing here, so this is not happening, and this row is also, so this is also false. So I hope like you got the answer of this one also. So this is the like complete assignment. All 10 questions have been done like in time. That is good. If you have any doubt in any of the questions, you can ask me now. Like I know, like I was moving slightly fast. Okay, then if there is no other doubt, maybe I'll discuss the reading material. So reading material is certain in Barto chapter 7 and chapter 12, which you can do And one more thing is like from next week, it will be function approximation. So maybe I'll give you a brief idea before leaving. So what happens in function approximation is, suppose I mentioned in code also that there will be a table, Q table. So you are storing this table as A. So if like number of states become too large or number of actions become too large, right? Then what happens is like this table will become very big and it will be hard to store this big table and update it constantly as we see data. And there might be, suppose if you are dealing in real space, even though like your state is like just x coordinate between 0 and 1, but we know like there are infinite number of values in between. So we cannot have like one cell for each possible state action value pair in that case, because number of states are essentially infinite. So this table will have infinite number of rows. We can discretize, but discretize basically point one, point two, like we can discretize this point simply to one. But issue here is like discretization means loss in precision. So if we discretize like this, we wouldn't have taken something like 0.15, which might have been optimal, we don't know. And if you discretize even further, but then if you include this 0.15, 0.25 kind of thing also, but maybe the optimal would have occurred at 0.125. So all those kind of issues are there. So there, what we do is we use function approximation techniques. So function approximation you might recall from mathematics. So essentially, what is Q value function? So I'll use Q. It is taking two input parameters S and A and returning a real value, right? So it's a mapping from state space, action space to a real value. So this is the function. So there are ways of approximating these functions, and neural networks are like one of the best function approximators. So they are also known as universal function approximators because there are some results that they can approximate almost any of the function given to them if like there are proper activations. And also like recently like there has been a lot of success. So RL plus deep neural network, this has achieved a lot of success in Atari games, and many other breakthroughs have happened. So this is known as deep RL, where we basically combine neural networks with reinforcement learning and get very good results. So in Atari games, what was happening? We were supplying the raw pixel of the game, and it was predicting. Suppose the game is there, like if a ball is there, you need to keep this ball. You don't want to let this ball go down, so you need to move this block right or left in order to do that. So action will be two, whether to move right or could be three, you remain at the same position. So raw pixels were getting supplied to this neural network, and on the basis of that, it was predicting the state. So how this happens is, suppose you have your state. Suppose your state is X coordinate, Y coordinate, Z coordinate, and this is a neural network. So input layer, like there are, you can have like state. Suppose if your state is three features, like we saw in that frozen lake example, our state was just X and Y coordinate. So two features. But here, suppose if there are three features, then you can have a neural network. And then last layer, you can have actions. So suppose if you want to move left or right, and it will give Q value for that. So in this way, like we can avoid those issues which are with these tabular approaches. So this is known as tabular approaches of RL. And what we are currently discussing is known as deep RL. So deep RL is basically like usage of neural network. So what will happen? So this neural network will essentially, you can give it any real values. It could be 0.11111, something like this for any of the feature, and it will still give an output. So you don't need to keep a cell in the table for each of such values. You can simply have a function approximator like a neural network, and it will like give for even for those values which you might not have seen before. So it will give for those also because it learns a mapping from this state space to maybe like it will give. So this is known as policy network if you are directly mapping to state to action. Otherwise, you can have Q network also, DQN. So it essentially maps to for each action, it will give a Q value. So those are like things which will be discussed in upcoming classes. So I hope like you get an idea like what is coming. So I think like that was it from my side today. So thank you everyone. If there is anything, doubt or anything, you can ask me. Otherwise, I'll close this session. Okay,
Sir,
yeah, welcome. Okay.
sorry, sir. One question.
Okay, just a
So
minute.
actually,
Your voice is like too low.
too low. Okay. So can you hear me?
Now, okay,
Can you hear me?
yeah,
Yeah.
I'll,
Is it better? Sir, in this in the you explained that in the deep learning combined with neural network, it will give better results. So my question is, the reinforcement learning, that layer, it will be part of the neural network, or it is like where it is being positioned in the architecture. Like for
yeah,
example,
yeah,
in deep neural network we have hidden layers, input layers followed by
right,
several
right.
hidden layers and then output layer. But in the where we actually position this RL layer in the architecture of
So
the
see,
neural
see,
network.
yeah. So RL is not part of neural network layer. Neural network
Okay.
is part of RL. That is the difference here. So
Oh,
essentially in tabular approaches, we were maintaining this table for Q values. Like this was a Q table. So for every state
okay.
action pair, we were having one cell and we were maintaining values there. But since the number of states and number of actions are so large, now we cannot maintain this table. So now what we'll use is neural network. So in neural network, we will be supplying the state features and it will give
Mhm.
us the output like Q value for each of the actions. So now like we, instead of this table, we are having a neural network. So basically what is happening, neural network is like coming within RL, not the other way around. So here
Okay,
like
okay.
neural network is like one component of RL in deep RL.
Okay. Got it,
And
sir.
like all the reward
Yeah.
calculation and all that is happening outside the neural network. And then
Outside
on
the
the
neural
basis of
network,
that, you can
but
update.
correct.
Hmm.
The policy updation and everything is happening within the RL, but outside of the NN neural network,
Yeah,
right?
but those neural network parameters will need updates in order to learn the perfect Q value function. So those updates, like although they are calculated in the RL framework, they get supplied to neural network also so that it can adjust their weights accordingly.
Okay. Okay.
You
Got it.
remember those back propagation and all. So those kind of
Yeah,
updates are
yeah.
needed. So
Correct. So the WW weight vectors and
yeah,
all,
yeah,
you back
all those
propagate the
updates.
error. Correct.
Okay,
Got it.
so I think that was it.
Okay. Thank you so much,
So
sir.
I'll
Thanks.
stop
It's a great
sharing
session.
my screen. Yeah,
Yeah.
welcome.
Yeah.
So now if there is no more doubt, I'll close the session.